Okay, I guess we'll go ahead and get started. Before I get into lecture today, I just wanted to cover a couple of things, like issues that I might be seeing with the homework. So, several people have asked about how to compute V infinity. And we've already mentioned that V infinity is the velocity on the hyperbola, essentially at the sphere of influence, where you're patching the two conics together. So, let me see if I can get this to work. So, V infinity is a velocity with respect to some planet, okay? Not plant, planet. And if we want to find, and we, from Lambert's, we have, let's say we have a departure velocity coming out of Lambert. So that's departing on a heliocentric velocity, right? Because it's the velocity on a conic with respect to the sun. So this departure velocity is with respect to the sun. Now, if we want to find V infinity, we can take the velocity at departure with respect to the sun minus the velocity of the planet with respect to the sun. Now, what we don't want to do, the magnitude of V infinity is not equal to the magnitude minus the magnitude. If you get that, you're essentially just subtracting their velocities, and you're not taking into account the direction of their velocities. So instead, you'll have, if you want the magnitude of V infinity, it's the magnitude of your departure velocity with respect to the sun. It's the magnitude of this quantity here. Does that make sense to everybody? So if you're getting a negative value for V infinity, take a look at your code and make sure that you're not doing this one, because we don't want to do. You want to take the magnitude of the difference of the vectors. That way you're accounting for the direction of the velocity and not just the speed. Okay? The second thing is on the homework with Vesta and series. When I gave 3 assumptions, you're not solving the problem 3 different times. Okay? It's not part A, B, and C. Some very enthusiastic people wanted to solve it 3 different times. It's just, you just solve it once with those 3 assumptions. And then, let me see, what other things were we having? Let's see here. Did that pull up my laptop? No. Did that not pull up? Okay. Wait a minute. Here we go. One issue that, I'm going to try and replicate this here in GMAT, and this might not be a bug in Windows or on the computer. It might only be on the Mac. GMAT sometimes has the annoying way of not applying corrections that you think they are, and this is especially the case with copy-paste. And I know that when there's really long sequences of numbers, especially like when we give the semi-major axis and the eccentricity, it's really common to want to just copy-paste. I'm going to see if this works, okay? So let's say I want to try and change my, I'm sorry that's so small, my x component to this really long number. So I'm just going to try and copy and paste it here. See how apply is still grayed out? I can click OK, but if I go back and look at that, it's still 5,000. So I was able to replicate it. If you want to do this copy-paste thing, what I would suggest doing is when you copy it, oh, hold on. Copy. Oh, there it was. So copy it and then add a keystroke at the end, like a space. Just for whatever reason, put in a space. Then you can hit apply, OK. Some people were having trouble with that. They thought that they were actually putting in the right values when in reality GMAT was not picking it up. A couple other things, just briefly to talk about integrators. Let's just say that we were to put in a state of the spacecraft that is, now this is in the Earth frame. Okay, let's just look at this. Let's just say we have these positions and these velocities with respect to the Earth frame. What does that tell you? Where are we?
In the center.
Inside the Earth, okay? Who has any idea what might happen if you try and throw this into an integrator?
It won't converge. It won't converge.
Yeah. When you're integrating, think about your force function. The force function that we have is something over a radius magnitude. Now, if your radius magnitude is very, very small, the terms in your integrator function are just going to blow up. And what's going to happen is if you've got a really tight tolerance on your integrator, so if I were to pull up this default propagator, it's going to try and match steps to 10 to the minus 12. So essentially what it's trying to do is it's looking at different steps of integration, and it's going to try and get your successive steps to match to 10 to the minus 12. If you're inside the center of the Earth and you're kind of near a singularity, essentially, it's never going to be able to hit that. And so your integrator might start getting into an infinite loop. So if you're seeing really long integration times within GMAT, within STK, within MATLAB, with whatever you're coding in, and something is just taking really a long time to run, take a look at, one, where your initial position is, or you could also take a look and see, well, hey, I started way far away, but maybe I ran into something. Like, maybe I accidentally am trying to integrate through Mars. Like, maybe my flyby is not taking me over Mars like I thought it was. Maybe I'm actually going through Mars. So just a couple of helpful tips. Hopefully will save you guys some headache. Are there any other questions about the homework or the labs? Yeah.
I have a weird thing where my V infinity is actually negative for problem 1, and so I don't really know how that could happen.
Oh.
I sent an email just like a few minutes ago.
Okay. Let me switch back to. When you're computing for V infinity, are you subtracting the components or are you subtracting two different magnitudes?
Two different magnitudes, I believe.
Yeah, so what you want to do is you want to subtract, to actually get V infinity, you don't want to subtract magnitudes because then you're essentially just taking the difference in speed and you're not taking into account the direction of the velocity. So to get V infinity, it's the magnitude of the planetary velocity minus the departure velocity minus the planetary velocity, not the difference in two magnitudes. Okay? Welcome. All right. Not that one. We'll do that in a minute. Okay. All right. Pull this up on both. All right. So hopefully you guys are, either have a working Lambert solver or you're really close to having a working Lambert solver. Now that I tell you that you have one, I am going to tell you that sometimes it will break. Okay? Anybody have any ideas as to when the solver might break and why it might not work? Yeah.
If you give it a really small time of flight window and like 1 rev or more, then it'll break because it's trying to go around the sun in 30 days and then make it to Mars. Exactly.
If you try and say, I want to go from Earth to Jupiter in 1 day, or 10 days even, it's not going to converge. Because if you'll notice, it's looking at a difference in tolerance that's down to 10 to the minus 5th seconds, and you're just not going to be able to find something like that. The good news is that I'm not going to ask you to solve for things like that in this class. And maybe it's an interesting academic exercise to see what a conic looks like that goes from Earth to Jupiter in 10 days. What kind of conic is that going to be?
Straight line.
Yes, it's going to look kind of like a straight line.
Hyperbola?
Yeah, it's going to be a hyperbolic. I mean, you're going to need a lot of velocity to get out of the Earth. Because I'm not going to ask you to do stuff like that. I mean, obviously, you would need a huge C3, and there aren't going to be any missions that are going to do that. So this Lambert solver with the universal variable bisection method that we are using in class will work really well for practical applications. And honestly, we're mostly concerned with practical applications. NASA really doesn't want impractical things. They tend to be very expensive. I guess the point of this is to code in some logic. You know, make sure that you're not looking at negative time of flights, for example. Because it's really easy if you're going through a for loop and you're trying to look at, you know, different planetary alignments. It might be really easy to accidentally, like if you're cycling through a whole bunch of launch dates and a whole bunch of arrival dates, especially for an Earth to Venus transfer, it might be really easy to accidentally come up with a negative time of flight. Just pay attention for those sorts of things and make sure that you don't have that in your code. Okay. So one thing that is really interesting to do is plot values of the variable psi versus time of flight. So one way to do that is, let's just say we pick a departure planet of Earth and an arrival planet of Venus. Now what we're going to do is, based on those states, now we're not going to let those states move. We have a position of Earth, we have the position of Venus, where now we're going to vary the time of flight and look at what different conics might look like based on those two positions, okay? And for each time of flight, we want to compute a corresponding value of psi. And remember, psi physically represents delta E squared. So this is what that plot would look like, okay? So we've got psi squared on the bottom, and on the y-axis we have time of flight in days. And for delta E or delta E squared or psi values that are negative, we're looking at hyperbolic transfers. If psi is exactly 0, it's a parabolic transfer. And if psi is positive to a certain extent, we've got an elliptical transfer. So what do you think this curve does at higher values of psi?
Circularizes everything. Like, can it become a circle? Like, if you have a value for parabolic, is there one for a circle? Like, is that a thing? If you have like high enough phi, is that what it is? This is like strictly out of curiosity on my part.
I would have to think about that. I don't know if you can ever approach a perfectly circular transfer because you're not starting and ending at the same radius.
Okay.
Because, you know, you've got different initial and final radii about the sun, and so I don't think you could ever have a circular transfer.
Okay.
Anybody else? Yeah.
I was just thinking, strictly, psi is only delta E squared in the elliptical case, right? Because you can't have a square root of a negative. So I think Volato defines some other m or something for the...
Yeah, yeah. For this universal, for the way it's formulated, if you get a negative value, then you're looking at a hyperbolic orbit. But if you think about, you know, delta E, you're looking at how delta E changes around. So if psi is getting higher, that means delta E is getting higher. What are we looking at?
You're going to have multiple revolutions?
Yeah, multiple revolutions. So this is what we're looking at. If we extend our plot, so let's think about it. If we have a transfer that is bound on a single revolution transfer, right? How many degrees is that? (360), right? So in radians, what are we looking at? 2 pi. 2 pi squared is?
About 40.
Well, 4 pi squared, right? That's essentially this bound right here. So as we get above 4 pi squared, we're looking at these elliptical 1 revolution solutions. So we can, in the initial Lambert solver that we had, does anybody remember what, at the beginning, we initialized values of psi. Does anyone remember what our initial values for psi low, psi up, and our initial value of psi were?
Minus pi squared and plus pi? Plus 4 pi, sorry?
Yeah.
Minus 4 pi squared and plus 4 pi.
Yeah, they were essentially these bounds. I think it was minus pi or minus pi squared and 4 pi squared. That way, when we're doing a bisection method, we're guaranteed to get something in here. Now, if we want to extend our search to multiple revolutions, then we need to change our initial values on psi within the Lambert solver. And we can actually get, 2, 3, 4 revolution solutions. And so the universal variable psi basically represents the following types. If we aren't going a full revolution, psi is going to go from 0 to 4 pi squared, and then it scales with n for each rev. And so you could compute, so here's 16 pi squared, and then you could just go on and on for extending 3 rev solutions. When a 3 rev solution would ever be useful in interplanetary mission design, I don't know. I mean, that's going to take a lot of time. It's interesting to think about, maybe interesting to compute and see graphically what it looks like, but it's probably not something that we would want to do because it's just going to take so much time. So now we see we've got more than just type 1 and type 2 transfers. Now we've got type 3 and type 4, where type 3 is going to go from basically 360 to 540, and then type 4 is going to go from 540 up to 720, and then type 5 and type 6, basically just incrementing in segments of 180 degrees. Does that make sense? Okay. And one thing I did want to note is the curves of this plot, the basic shape is going to stay the same, where you've got, this kind of almost parabolic or hyperbolic looking shape here, and then kind of, almost parabola-like shapes. They will shrink or shift or expand based on the different departure and arrival points. Because, obviously, where you actually have a hyperbolic time of flight is going to be different based on the positions of the planets. So different books are going to use different nomenclature. Unfortunately, there's no set standard. So sometimes, like with the 0 rev case, we can refer to as the short way or the long way, essentially type 1, type 2. But with 1 or more complete revolutions, there's basically 4 options. You can go the prograde way around, where it's the odd type transfer, like type 3, type 5. Or you could go the retrograde way around the orbit, where there's type 3, type 5. Or you could go prograde. So you've got prograde, retrograde, even or odd type transfers. So you could have transfers over here that go prograde or retrograde, transfers over here that are prograde or retrograde. Hopefully that kind of makes sense. In this class, I guess some people refer to this as like your left branch solution and your right branch solution. Okay? Different, I forget what Bate-Mueller and White refers to them as. In this class, we're simply going to do type 1, type 2, type 3, type 4. And we're always going to assume prograde motion. We don't really need to mess with retrograde solutions. They are kind of interesting to look at, though. So here are some example transfers from Earth to Venus. Each transfer is essentially starting at the green star and going to the red star. And so I've got the prograde solutions on top and retrograde solutions on the bottom. So because I can't reach the top, I'll just kind of demonstrate this. So if we were going retrograde from Earth to Venus, the long way around, we're basically going like this. And if we're doing retrograde, the long branch here, all the way around and back. If you want to look at a type 3 transfer, this is kind of what it looks like. Here's the type 3 transfer from Earth to Venus. It takes 850 days. So here, I've also plotted the distance to the sun so you can kind of see what's going on. So basically, we start at the Earth, we cross Venus's orbit, and then most of the transfer, basically from 100 to 800 days, 700 days, are essentially on this really long portion where you're going really slow. And then you eventually get back to Venus. Here's a type 4 transfer that takes 850 days. Again, we've got our heliocentric distance and the distance to the sun. This one, you can see it looks much more feasible than the previous one. You know, this previous solution, you're really burning against the direction of the Earth when you're departing, and you're not really hitting Venus at a tangential direction, right? Like, it looks like a pretty crummy transfer if you wanted to use this for interplanetary mission design. This one, not so bad, right? I mean, look how tangentially you're kind of coming into Venus. And here, you're leaving pretty decent with respect to Earth. Here's a type 5 transfer. So this is where you're making two revs. Again, not that useful, kind of interesting to look at, and a type 4 transfer for 850 days. So the way that our current Lambert solver works is it has initial bounds on psi, and it's completely based on the 0 rev solution. That's what we kind of described. And we're iterating using a bisection method. So I kind of wanted to take a look at how this works on a psi versus time of flight plot. Okay, so here's the single rev Earth to Venus transfer. Let's say that we want to converge. We know that we want to get from Earth to Venus in 100 days. So I've kind of represented that by this red line. So we're looking for this psi value. Okay, so if we were to look at the iteration sequence, it might look something like this. So our initial guess, if you remember, we initialized it as 0. So here's the first guess, 0. Obviously, that's too low. So what it's going to do is it's going to take half of this distance here. Remember, it's psi up plus psi low divided by 2. So now we get part 2, and this section is essentially rejected for where the solution might be. And then point 2 is obviously way too high. That time of flight is, you know, roughly 800, where we're looking for 100 days. So it'll get rid of this region and pick something in the middle at number 3. And we kind of keep going from 3, 4, and we essentially we're just getting closer and closer to the solution, cutting our step size down. Now, to reach a time, we set the tolerance at 10 to the minus 5th seconds. We want our time, the time we're computing within our Lambert algorithm, to match our desired time within 10 to the minus 5th seconds. Like, if you think about that, it's a pretty tight tolerance. And it took 42 steps to get there. And this is just a history. So at the very beginning, we were obviously off by 700-800 days, you saw. But after 42 iterations, we're down to that 10 to the minus 5th tolerance. Way back in the day, that was when computing time was actually more at a premium than it is now. This was an issue. So some people wanted to use a Newton-Rapson method for speed, and the function there is approximated by a tangent line. So if we look at the same curve, you look at your initial starting guess and you approximate the slope there as a tangent, and then you can look at different tangents until you narrow in. So we see that that tangent's not where we want, so now we're up above. This one only took 6 steps to reach the tolerance. The problem is that this can break in certain circumstances even more easily than the bisection method, especially for hyperbolic orbits. And with current computers, it's not really a huge speed up, so the robustness factor might be preferable to this. If you want to speed up your code in the future and you know that you're going to be in elliptical regions and you're going to be computing a lot of data, this is something you might want to take a look at. So based on our current Lambert solver, we need to make some modifications to account for multi-rev. So first, what do we need to do?
Increase the psi up boundary.
Okay, we need to increase the psi up boundary. What else?
We have to tell it how many revs we want it to look for.
Yep, we probably need to tell it how many revs we want it to look for. Okay, so we want to change our initial bounds on psi and then pass in an input for the number of revs. Does anyone remember what the curve looked like for multiple revs? So that, well, let's talk about the curve for the single rev solution. What's the slope? For that single rev solution, let's go back to, what's the slope of this curve? It's always positive. What about our multi-rev solution? It's negative at the beginning. So you're going to want to put in some internal logic, because obviously that bisection method, taking psi up over psi low, is not going to work for this type 3 or this type 3 transfer. It's going to work on the even side, but not on the odd side. So you're going to want to put in some internal logic to, it's up to you how you do this. There's a few different ways to do it. But basically, a good way might be to pass in the number of revs and whether you're looking for a type 3 or a type 4 transfer. Once you have that, then you can figure out which equations you want to modify on the psi up, psi low front. Basically to make a negative slope rather than, basically you're looking for the negative slope instead of a positive slope. Okay, so just in summary, the Lambert algorithm presented in class it's pretty robust. It's not as fast as a Newton-Rapson method, but with, like I said, with the computing power these days, it's fine. There are some modifications that we need to do the multi-rev solutions. It's up to you completely whether you want to have one function that will do all cases or have a function for 0 rev and a function for multi-rev. Completely up to you. I personally have 2 different functions because I don't like to have a lot of if statements within my code. I think it slows it down, especially if I'm searching over large portions of data. And when we're looking at, let's say, the final project, and you're looking at transfers out to Neptune, you're not going to be looking at multiple rev. You may need, there are some really great transfers that use multiple rev solutions from Earth to Venus, because you can wait for Venus to get into good alignment, and it doesn't take that long. You might spend an extra 80 to 100 days, but if you're going to cut your C3 by 10 or in half, then it's very useful. It's great to check for the type 3 and 4 transfers, but it's getting long for most applications. The homework for this week, let me see if I can pull that up. You're going to compute the positions of Mars and Jupiter based on certain dates, and I want you to create a plot like this multi-rev plot, the psi versus time of flight, and show the different regions on the plot. Basically, you're recreating a plot like this. This is the plot for an Earth to Venus transfer. So, like I said, the one for Mars to Jupiter is going to look different, but it's going to have the same shape. And then we discussed this in class already, so hopefully this is a gimme. What has to be changed in your universal variable solver to get multi-rev? And then I want you to compute the shortest time of flight in days. So basically, that minimum on the red curve, the minimum time of flight that you need. Okay? Any questions on multi-rev? Okay? Okay. Then bear with me here. This will be the first time I've tried to give a lecture using the pen and the lectern, so hopefully it goes well. For the flyby, we're going to talk about gravity flybys now. And for gravity flybys, this is the kind of stuff I like to write out because I think it's really helpful to have drawings at hand and to actually be able to draw it out yourself and see what's going on. So first I need my pen. Okay. Let's go. All right. If you can't read my writing, let me know. And then I will try and saved all this. Okay. So a gravity assist, or sometimes we would call it a flyby. I just wanted to go into the history of this because I think it's really fascinating how scientists and astronomers really looked at physically what was going on in the skies and tried to understand it based on the models of the day. So there was a lot of classical astronomical work. Anyone have any ideas what they might be studying if they're looking at gravity flybys?
Asteroids?
Yeah, pretty much. Or
Comets.
comets, yeah. So to understand perturbed comet motion. So these astronomers were observing comets, and they weren't staying in the orbits that they thought they were, and they couldn't figure out why. And the best example we have of this is Comet Lexel. And what they basically found out is that it passed near Jupiter, and its orbit was just radically altered. So for the rest of this, I'm going to be using that for Jupiter. And when we talk about radically altered, when they first observed Comet Lexel, it had a semi-major axis of about 13.3 AU, and that was around 1767. Later, when they saw it, it had a semi-major axis of 6. So clearly, something happened between 1767 and 1779 that just really changed Comet Lexel. And what they found were that Lexel did a flyby of Jupiter in 1767 and 1779. And actually, between flybys, between the flybys of Jupiter, it actually flew by the Earth. That's why they were so interested in this comet. Mainly because it passed within 0.015 AU of Earth. So at the time, it was the closest body that had ever passed near the Earth. After that flyby of Jupiter, in 1779, the comet was never seen again. So basically, that flyby of Jupiter, it got enough change in its velocity and its energy to be ejected from the solar system. Or maybe it's just on a really, really, really long elliptical orbit and it hasn't come back yet, but they think it's been ejected from the solar system. They think it may be on a hyperbolic orbit. It hasn't been seen since. It's a lost comet. Okay. So around this time, Leverrier, he realized that these orbits are modified by hyperbolic encounters. Meaning that while you're on a flyby, the spacecraft, the comet, whatever, as it flies by the planet, it's on a hyperbola with respect to that planet. It's not on an ellipse because it's obviously not getting captured by the planet. So, it's on a hyperbolic orbit. And he also noted that it's changed, that after this gravitational flyby, that it's changed the orbital energy with respect to the sun. And that's really what we're looking for, is changing our orbital energy with respect to the sun. Like if we want to get someplace more quickly, or if we want to harness the gravity of other planets, we want to change our energy with respect to the sun. A man named Tisserand, I guess a little backstory, when they saw Comet Lexel those 2 times, and one time it had a really high semi-major axis and the other time it had a much smaller semi-major axis, there was a controversy as to, well, how do we know this is the same body that we're actually observing? Maybe it's something completely different. So Tisserand, he came up with this criterion to determine if an observed body is the same as a previously observed body. So if you could take some measurements, you could see, well, is what we just saw, is this the same asteroid we saw before? And he came up with Tisserand's criterion. So he used the semi-major axis of the first, the eccentricity and the inclination, and he said, if you were to compute this quantity for the first, it should essentially be equal to this same quantity for the second. Or in other words, this 1 over 2a plus the square root of a, 1 minus b squared times the cosine of the inclination is approximately constant. So then they were able to determine, that these comets were the same. Okay. Between 1920 and 1957, let's see. Okay. So that was kind of the classical astronomy in the 1700s and the 1800s. In the early 1900s, so let's say 1920 to 1957, a man named von Perturbed, he used vector diagrams, which will hopefully become your friend, to model flybys. And to show modified energy. And around this time, there were also a lot of science fiction writers, and they kind of, in a qualitative sense, understood what was going on. The science fiction writers were using flybys in their solar system exploration. They might not have had, all the physics entirely right, but there were a lot of stories out there where these brave explorers were using gravitational flybys to get to distant stars or planets or whatever. And then, basically since 1958, there's been applications of flybys. So the basic idea of a flyby is to alter the spacecraft's energy with respect to the sun. So we're also essentially getting what we'll call free energy. Flybys, as we saw in the very first lecture, I talked about Ulysses. Anyone remember what Ulysses did?
Fly by the sun.
It flew by Jupiter to get to the sun.
Over the sun.
Yeah, to get into a polar orbit about the sun. So you can use flybys to change inclination. So we'll just see the Ulysses mission. Okay? One thing that we do need to note about flybys is that angular momentum is conserved. Okay, so let's just say that we are flying by a planet and the spacecraft's energy with respect to the sun is going up. So what's that going to mean? if our angular momentum is conserved.
Planet you're going about is losing energy with respect to this.
Yes. So the planet's energy with respect to the sun is going down. So if the spacecraft's energy with respect to the sun decreases, then the planet's energy will increase. Okay. Now, are we worried about the energy change of the planet? Like, is sending spacecraft, doing multiple flybys of the planets just going to throw the planets into chaos because they're losing energy? Like, are we dooming the solar system by what we're doing here?
You had the Death Star, maybe.
Huh?
You had the Death Star, maybe.
Maybe, if we had that would be awesome. That would be a really interesting physics problem. Like, I'm just thinking about this in my head now. Like, okay. Rather than blowing up planets, we're just going to send them on. We're just going to eject them from the solar system. Okay. So are we worried about our spacecraft doing that? No, we're not. We are not worried. So, not worried about the energy change. Why is that?
Mass is negligible.
Yeah. Yep. The mass of the spacecraft is much, much less than the mass of the planet. It's essentially negligible. Okay. So, let's talk about what actually happens inside the sphere of influence. So, what happens inside the sphere of influence? Okay? So, inside the sphere of influence, the spacecraft enters, this is important to understand, it enters and leaves the planet's sphere of influence with the same energy relative to the planet. Okay? So relative to the planet, as the spacecraft comes in on this hyperbolic trajectory, it's the same hyperbola as you enter and leave, right? So no energy change. Okay? The flyby is hyperbolic. So we can say that at infinity, let's just use the energy equation. Energy at infinity is going to be V infinity squared over 2 minus mu over r is minus mu over 2a. Well, we can kind of say that this is r infinity, right? So what's going to happen to that term? Yeah, this term essentially goes to 0 because r is infinity. Now again, we're just making an approximation that's not entirely true, but we can say that energy is now V infinity squared over 2. So just to let you know, I'm going to use the notation plus to be outgoing at the flyby and a minus sign to be incoming at the flyby. So we can say that energy coming into the flyby is V infinity coming in squared over 2. Energy coming out is also V infinity squared over 2. So we have, since we don't have any energy change, V infinity in is equal to V infinity out. Okay? Everyone have all this before I go to the next slide? I'll just give you a minute. Now, again, I'll just put assumes no perturbations. doing on time. Good. So for our preliminary mission design, assuming no perturbations is a good approximation. Okay. So we've said that V infinity in equals V infinity out. Sometimes people will, say in and out. But does that mean that is that statement true? No. This statement is not true because we're changing directions. Our flyby vector is turned. So that is not true. The magnitudes are the same, but the velocities are different. So components of velocity are different. Okay, so let's just look at a vector diagram here. Here's our planet, and here's the velocity of the planet. All right, so let's just say we've got this nice hyperbolic trajectory. You've got V infinity in and V infinity out. So let's draw a vector diagram for the flyby. So we'll start at, we'll just put the sun here. So here is the velocity of the planet, and that's with respect to the sun, okay? Now, V infinity in and out are with respect to what? The planet, okay? So let's just draw, here's, kind of looks like it's going in that direction. There's V infinity in, and here's V infinity out, okay? So, and I tried to draw those the same length because they're the same magnitude, right? So, from our Lambert solver, we have our departure and arrival velocities with respect to the sun, okay? So here we've got, this would be V arrival at the planet. So that's the hyperbolic, or sorry, the heliocentric velocity as you're coming in on your conic orbit. And then here is the departure velocity with respect to the sun. Okay? So V arrival, it's the velocity on a heliocentric orbit. So that's the transfer orbit that you would get from Lambert's. Okay? And velocity at departure is the velocity at arrival, sorry. This is on a heliocentric orbit at departure. Okay? So sometimes we'll just call, we can also say that this is the spacecraft's velocity with respect to the sun at departure. And this would be, V arrival would be the spacecraft's velocity with respect to the sun at arrival. And so now, hopefully it's really clear that you can see that V infinity incoming is just the velocity at arrival minus the velocity of the planet, and V infinity outgoing is the velocity at departure minus the velocity at the planet. And so now what can you see about the two departure and arrival velocity vectors, at least magnitude-wise?
Departure's bigger.
Yeah. So just looking qualitatively, we've really increased the magnitude of our departure velocity by this flyby. Okay? So let's just kind of talk through, does everyone have this? Okay. let's talk through how we're going to get all these velocities. So let's just do, let's do an example mission from, let's go Earth to Jupiter with a Mars flyby. Okay. So essentially Earth to Mars to Jupiter. So how are we going to, so we're flying by Mars. How do we find all these velocities? So for the flyby, we need v infinity in, v infinity out, velocity at arrival, and velocity at departure at Mars. So how do we find all those things? So what can we find? Let's say we're given the dates. Let's just say we're given the dates of the events. So we know Earth launch, Mars flyby, and Jupiter arrival dates. What can we do?
Velocity of the planets.
Okay, we can get the velocity of the planets. So we can get the velocity of Earth, the velocity of Mars, and the velocity of Jupiter. What else can we get?
Lambert gives the arrival velocity.
Yeah. So how do we get the arrival velocity? Where would we solve Lambert's? Which two would we use? We want the arrival velocity at Mars. What are we putting into our Lambert solver?
Position of Mars.
And Earth, yeah. So we'll solve Lambert's from Earth to Mars. This will give us our velocity of arrival at Mars. All right? So from v arrival at Mars, then we can get our incoming v infinity, because we've got our velocity at Mars, and we've got the velocity of Mars itself. So what about our departure velocity?
From Earth? Or from Mars?
From Mars.
Okay.
If we're going to, what's the departure velocity out of Mars? How could we get that?
Vector diagram?
We could maybe do a vector diagram. Let's think about that. So if we wanted to do a vector diagram, right now we've got v infinity at Mars and v infinity, or we only have v infinity at Mars, and we only have our arrival velocity at Mars.
You need to know how close you're going to get to Mars, right?
How could we solve for that?
Turning angle?
Well, if we don't have v infinity out, we know the magnitude of v infinity out, but we don't know the components. So if we don't know the components, then we can't get a turn angle.
We can solve Lambert's problem for Mars to Jupiter.
Yes, we can solve Lambert from Mars to Jupiter. And then that will give us our velocity departure at Mars, and so we can get v infinity outgoing. Okay? So now we've got our flybys. Now, the diagram I drew before, we showed kind of our departure velocity looked larger than our arrival velocity. So we've essentially got two ways to fly by the planet. So if this is our planet here, we've got the velocity of the planet. We can fly by like this, where we've got v infinity in, v infinity out. Or we could fly by like this, where we've got boom, boom, and V infinity out. All right, so I'd like you guys to work together, or not work together, but in groups by yourselves. Just do a little in-class exercise. I'd like you to draw the vector diagrams for both of these cases and look at energy changes. We'll call this a pass ahead or a leading.
Pass ahead.
And a pass behind over here. Okay. I'll give you guys a few minutes.
Pass ahead, you slow down. Pass behind. That shit from. No, the vector diagrams. Oh, there it goes. Share yours. So, velocity of the planet, V infinity minus, V infinity minus, V infinity plus, V infinity plus, V part, V arrive. See that?
Okay, so which of these flybys, the pass ahead or the leading or the trailing flyby, is going to lead to an energy gain? If we want to gain energy, which way do we want to fly by the planet?
Behind it, trailing.
Behind the planet. And if we want to lose energy?
Front of.
Yep. So I'll just draw them real quickly. Let's just say that let's just do the behind case. So here's the velocity of the planet. I tried to make this like vector diagram somewhat easy. So here's V infinity minus, V infinity plus going this way. So here's our velocity at arrival and our velocity at departure. So here we've got trailing. And we've got an energy gain. Because the magnitude of V departure is going to be greater than the magnitude V arrival. If we look at the leading case, again, the velocity of the planet, here's V infinity incoming. Oh. Aha, okay. But now V infinity out is this direction. So velocity at departure is smaller than velocity at arrival. So for the leading, we have, try not to like bump it with my hand here, energy loss. And our velocity at departure is less than our velocity at arrival. When might we want a leading or a trailing flyby? Let's talk about the leading flyby. Why might we want that?
Trying to get planets that are closer to the sun.
Yeah, get to planets that are closer to the sun if you want to try and slow down, essentially. And obviously the converse is going to be true for going out. All right. So now we've got a way to get the incoming velocity and the outgoing velocity with respect to the sun. We can figure out our velocity, our hyperbolic velocities with respect to the sun. Now we need something very important when doing a flyby. Anybody? What's very important when doing a flyby? Yeah, you don't want to hit the planet. So let's talk about how to get the radius with respect to the planet. So for that, I'm going to provide nice little hyperbolas to draw on because I think it's just nicer that way.
Thanks, man.
And we're going to try this guy here. Hopefully we'll try this. Oh, okay. Zoom out. Ooh, there we go. It's kind of nice not to get chalk dust all over my hands. I mean, it's not so bad.
You want to put this with the other extras? Thanks.
Did anyone have any questions on those vector diagrams? Do they all make sense just from a nice geometric point of view? Okay, good. All right, so first let's just start by labeling some parts of the hyperbola. So if we're looking at this distance right here, anybody? Periapsis. So we'll just call that R sub p. That's what we want to find out. How do we get R sub p so we don't crash into the planet? Okay? This value here, if we were to drop a perpendicular line right at periapsis, this value is b, the semi-minor axis. And then this value is the semi-major axis. And this tangent line right here, if we've got A and B, anybody have any brilliant guesses as to what this tangent line is? C. Okay. So for the hyperbolic equations, the general equation for a hyperbola is x squared over a squared minus y squared over b squared equals 1, where c squared is a squared plus b squared. One thing to note for hyperbolas, just by definition, is that the semi-major axis is what, positive or negative? Negative. So we'll say that r sub p, we can define that as a minus c, but we have to note that both a and c are less than 0 for a hyperbola. So let's just define it this way, where we've got our incoming v infinity vector and our outgoing v infinity vector. All right, so now we're going to start looking at the turn angles. Obviously, these dashed lines are the asymptotes of the hyperbola. And if we define an angle between the line from the origin through periapsis and the asymptote, we'll call it rho. So these values are rho, and we'll define rho as the asymptote half angle. Oh, sorry if this is sliding down a little bit. Let me zoom out just a smidge. If you can't see something, just let me know. Hopefully we can. Oh, probably. Okay. Now we're also going to define. So the angle through which v infinity in is turned to v infinity out, we'll call the turn angle psi. I know that's confusing. This is different than psi of Lambert's. Okay, so psi is the turn angle. It's different than Lambert. So, conveniently, we can write a relationship between psi and rho. What would that be? Psi is pi minus 2 rho. All right? Now, we want to eventually get the radius of periapsis. And we have the radius of periapsis as a over c. So let's see if we can work with that. So we can define the cosine of rho is a over c. And we've already said that r sub p is a minus c. So let's make some substitutions here. So we'll do we can now make 1 over c over a, and then do 1 over a minus, we'll do a minus c over a. So now we've got something in terms of the semi-major axis and the radius of periapsis. Okay? We're going to multiply by mu over mu and rearrange. So we'll have 1 over 1 minus, we'll take mu over a times r sub p over mu. So basically I just multiplied by mu over mu and rearrange this. So now we can take a look at the energy. The energy of a hyperbola is just v squared over 2. And then remember I said minus mu over r goes to 0 because we are looking at infinity. And this is also equal to minus mu over a. 2a. That's right. So if we were to rearrange this, we can basically just say that v infinity squared is minus mu over a. All right, let me zoom out. Okay. Yeah, we have time. Okay. So let's substitute this equation back in here. So we'll have cosine rho is 1 over 1 plus v infinity r sub p over mu. And if we can recall that psi is pi minus 2 rho, we can substitute that back in. So we'll have rho is pi minus psi over 2. Let's pull this out over here. Let's just kind of rearrange this. We'll have 1 plus v infinity r sub p over mu is equal to 1 over cosine of rho. Yeah. Thank you. Yes. So 1 plus v infinity squared r sub p over mu is equal to 1 over the cosine of pi minus psi over 2. So we're getting really close to getting somewhere. No. That's as far out as I can go. All right, I'm going to scoot this up. We can solve this for r sub p, because that's essentially what we're looking for. So we'll have r sub p is mu over v infinity squared, 1 over cosine pi minus psi over 2 minus 1. All right. So we've got this nice equation for r sub p. We know v infinity squared. What we need to find is psi. We don't know what psi is. But hopefully we can show this real quickly. I'll just show an alternate view of a flyby. So if we've got a flyby that's doing something like this, here's r sub p. You've got v infinity in and v infinity out. Here are the asymptotes. This is values of rho. And here's psi. We can actually find psi from v infinity in and v infinity out. I'll do that up here. Sorry for the running out of room. So find, okay, we can see that. Because we know the components of v infinity in and v infinity out. Because v infinity in is essentially, it turns into v infinity out. So we can just say that psi is the arc cosine of v infinity in dot v infinity out over the magnitudes. So we've essentially solved our flyby problem. We've used Lambert twice to get our departure and arrival velocities. From our departure and arrival velocities, we can solve for v infinity in and v infinity out. Then with the components of v infinity in and v infinity out, we can use that top equation to get psi. Once we know the value of psi, we can plug it into this handy equation here and get our radius of periapsis. And we can confirm whether or not it's a valid flyby. Because you can plug in arbitrary dates for Earth, Mars, and Jupiter, and you'll find that for certain dates you're going to hit the planet. It's not guaranteed that you won't hit the planet. But now we have a way to actually figure out whether we do or not. So with that, we'll stop for the day, and we'll see you in lab on Wednesday. And we'll start looking at non-Hohmann transfers to Mars in GMAT.
-1 in the RP equation at the very bottom, is that